The wonderful thing about Tiggers, and Tiggers are wonderful things, their tops are made out of rubbers, their bottoms are made out of springs. They're bouncy, 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 fun, 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 fun. We're looking at F equals MA. Unit 6, problem 20.3, and in it we're looking at forces, specifically, once again, spring forces via Hooke's law. So what we have here in our practice problem is a spring with a spring constant, so the strength of a spring, K, of 15 newtons per meter, hangs vertically from a ceiling. A 1.2 kilogram mass is attached to the bottom end of the spring, and it's allowed to hang freely until it becomes stationary. Okay, so it's reached a new equilibrium position. Then the mass is pulled downward 10 centimeters or 0.1 meters from this equilibrium resting position, and then it's released. At the moment of its release, so instantaneously, what is the magnitude of the mass's acceleration? And then what's the direction of that? We're going to ignore the mass of the spring here, thank goodness. Okay, so let's just draw a picture. Grandpappy Potzer needs a picture. Spring, 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 spring. Mass at the bottom. And we've pulled it down, we've pulled it down 0.1 meters, 10 centimeters, okay? And we pulled it down here. If we pull the spring down, we know when we let go, it's going to bling, it's going to bounce back up, right? So we know it's going to go up like this. So what we just need to ask ourselves now is, what direction would we like to call positive? What direction would we like to call negative? So I like calling the direction of motion positive. So I'm going to call up positive, and that means down is going to be negative here. So this value for the 0.1 meters, this x, I'm actually going to call that a negative value because I pulled it down. Okay. Now, if we take a look at this here, sometimes this problem is a little bit confusing. Sometimes people want to start including the weight into this, and you actually don't need to. In fact, when we look at this, the only force acting on our setup here is this spring force going up. And it's not an entirely true statement, but that's the only force we care about. And let's see why. If I had over here my spring, and I put a block at the end of it, and then I let the block, I let the string stretch because of the block, the spring has stretched because of the block and it's hanging there, then the weight acting down and the spring force pulling up here are equal, right? The block's not moving anywhere, it's in an equilibrium position. It's got zero acceleration. So that's that. I don't care about anything else. So I can almost think about these forces as just going away. What I really need is, when I stretch this a little further, I gain a little bit more spring force here, and that's the one that's going to cause this to start bouncing back up and down. Okay? So that's the spring force I care about. So when I set the sum of the forces here, I don't need to consider the original spring force or the weight, because they have canceled each other out. Okay? If I did put them in, they'd go away completely. So the only thing I need to worry about here is this one spring force due to my extra distance I pulled. So in this case, when I'm setting up my F equals MA, I can simply say minus KX equals MA. And in this case, we know some values here. Let's see, we're looking for the acceleration. We know that K, so there's our negative, we know K is 15. We know X here, we pulled it down, that's the negative direction, it's negative 0.1, so negative 0.1 equals, we know the mass here, the mass is 1.2 kilograms, so here's our 1.2 kilogram mass times acceleration. We quickly see that a negative times a negative is a positive, that's nice. 15 times 0.1 is 1.5, and then we divide by 1.2 on each side to give us an acceleration. 1.5 divided by 1.2 is just 1.25 meters per second squared. And that acceleration, as we already thought about it, since we stretched the spring down, it's going to be moving it up. We got a positive answer for that because we called up the positive direction. And that's it. The problem's done. So a kind of quick problem there, nothing too crazy. The kind of weird part of it was just thinking about how we didn't need to concern ourselves with that original little stretching of the spring from the block. Once it reaches an equilibrium position, we can just start the problem from scratch right there and only concern ourselves with the forces that are added beyond that equilibrium. Okay? So with that, this problem is finished. Adios, and take it easy.